First step, because it's statically determinate, we only have those two bearings. They're only exerting vertical forces. We can solve for the force due to those two bearings. We have the bearing at A. We have a 40-pound force 20 inches away. The bearing at B, another 20 inches away. And then the load of 60 pounds at the end, another 20 inches away. If we go through and solve this, we get that the reactions A is negative 10 pounds and B is positive 110 pounds. A can be negative, because either one can be positive or negative because it's a bearing, so it can prevent motion up and it can prevent motion down. So that's just from EMCH 211. Now we go and we make the internal cut so that we can get our M of X term. Again, we're making our picture at the extreme right, but we're using it as a representation to get M of X in general. So I'm cutting it right before that 60-pound force, just to the left of it. And I need to copy all of the reactions I have on this beam. I have the force from A, which was 10. I'm going to draw it in the correct direction for this diagram. So it was actually down. I have my 40-pound force. Oops. I have B is 110 pounds up. So what I do here is I always cut at the extreme right, and I always measure X from the left-hand side. From here, I now want to get what the sum of moments are around what I just call point C. It's where I'm taking that cut. So the first thing is always the internal bending moment, M of X. And now this is the difficult part, because I have to say that this equation I'm making is good for all values of X. So I drew it here at the extreme right because this will let me do that the easiest. But the equation also is, if I made a cut 10 inches in, if I take my M of X and I say put 10 in for X, I need to get the right value for M. So instead of actually drawing every possible picture, I'm only drawing the extreme case and using that to derive the entire equation. Right? So from this picture, how far is point C from the 10 pounds? It's X. Right? This picture is good for any value of X. So what we're doing is we're always placing the cut surface X away from the left-hand side. So I drew the picture this way because it's it'll capture every possibility, or this way we can look at one picture to derive the equation, but the cut surface is X away from the left-hand side. Yeah.
So do we ignore that 60 pound?
We ignore it in this picture because we are the furthest we can go to the right is just before the extreme right.
Yeah.
So this is the furthest that our internal cut can ever be from the left-hand side. Right, so the thing to remember, point C is X away from the left-hand side, even though in this kind of prototype picture, it looks like it should be 60. But it's a generic picture that I could shift this closer and closer and closer, and the equation I come up with is still going to be good. So with that in mind, if point C is always X away from the left-hand side, what is the moment due to the 10-pound force around C then? Right, it's going to be 10 times X positive. Again, point C could be here, and that is still good because 10 is X away from that cut. When point C is at, say, 25 inches, it's 10 times 25 inches away from the cut surface. And in this extreme picture, where it's about 60 inches away, the moment would be 10 times 60 around point C. So the point C is always x away from the 10 pounds. Right. So that's not too bad. Now it gets a little worse. So the 40 pounds, what is the moment due to the 40-pound force around point C? Right, it's a force of 40, but the distance now, again, say point C is 25 inches away. That means that x is 25. The 40 is only 5 inches away. So it's a distance from C of x minus 20. So what we always have is kind of this offset that we include when we have a point load or a couple or the start of a distributed load. So in this case, we have an offset of 20 from the left-hand side. For the 110, we have an offset of 40, which we'll use in a second here. Now this is where the singularity function becomes important, because again, what happens when x is, say, 10 inches? Well, let's draw that picture. When x is 10 inches here, I don't see this 40. If I just used x minus 20 and I put x is equal to 10 inches in, this is not correct because it's not even in the picture. It should not be exerting a moment when I'm taking everything to the left of my cut at 10. So this is where I use the bracket function or the singularity function, because now if I'm before the 40 pounds, I draw that picture, it's not in my picture. The bracket function ensures that it's not, because anytime the stuff inside the bracket is negative, this quantity is going to be 0. So now my picture is good whether I'm to the left of the 40 pounds, like a picture like this, or if I have a picture to the right of it, where now I do want to include that 40 pounds. This has the ability to turn it on when it needs to be on. And this is also going to create a positive moment around point C. Right? And finally, I have a moment that's going to be due to the 110-pound load. It's going to be a negative moment around point C. Right, same idea as before. It has, well, I'm going to call this offset of 40 inches. So it's going to be x minus 40. But again, I don't, like in this picture, I can't see the 110-pound force. It doesn't contribute to the moment internally in this picture. So again, I want a bracket function there so that it only turns on once I pass x is equal to 40 inches. Right, so I've accounted for the moments due to, in this case, all I had were 3 point loads, and they've all been accounted for. Right, so now we want to rearrange this because I want EI times d squared v over dx squared, which is the same as m of x. Which means I have to rearrange this and solve for m of x, which means I have to put everything else on the left-hand side. So this would be negative 10x minus 40 x minus 20 plus 110 bracket x minus 40. Don't jump right to this step. Always start with the moment around the point equaling 0, then shift it over so that you can solve for what that internal moment is. At this step, if we were to plot this in MATLAB or Mathematica or whatever, this is the M diagram for your VM diagram. It's exactly the same line you would see as if you did it by hand using the method we were looking at when we did VM diagrams. So we have the moment defined as a function of x. Now we can integrate it so that we can find the slope as a function of x. Right? So again, we're integrating polynomials. Negative 10 times x to the first will become negative 5 x squared when we divide through by 2. Right? The next term, we're going to raise the power of the bracket function to 2, which means we have to divide by 2. As we saw before with bracket functions, we can treat it pretty much the same way we treat just a variable. So I raise the power of the bracket by 1, and then divide by that power. Divide 110 by 2, raise the power of the bracket by 1. And this is an indefinite integral. I have to have that C1 term. Right? With that done, I integrate it a second time. Right? So I integrate dv dx, and I just get to v, which is my deflection. So I take what I just did, and I integrate it one more time. I have my slope equation with a constant of integration. I have my deflection equation with two constants of integration. So the calculus steps are over. Next, I want to solve for C1 and C2, and I do that using my boundary conditions. So for this problem, what are my boundary conditions? Where A is, we know the deflection is 0. It can't move up or down. And at B, we know the deflection is 0 as well. So our boundary conditions for this problem are that the deflection at x equals 0 is 0. And we know the deflection at 40 is 0 because that's where B is located. So these become our two algebraic equations to solve for, in this case, C1 and C2. So what we do is for the first one, we'll start here. It's usually easier when, if one of our x values is 0, it's usually easier to start there. So we want to set v of 0 equal to 0. So that means we use this deflection equation here. We know that EI times v of 0 is equal to 0. And we also know that it's equal to this right-hand side, but we put x equals 0 in for everything. So if we look what we have, this goes to 0. Here we have 0 minus 20, but since it's in a bracket, anytime it's negative, it goes to 0. Again, we have a negative in here, so this whole thing goes to 0. We have a C1 times 0 goes to 0. So all we're left with is C2. Again, well, I reiterate, we put in the value 0 in for x. So here we do have 0 minus 20 is negative 20. But again, the brackets mean if we have something negative inside the brackets, we just say it's 0. If we have something positive inside the brackets, it's whatever that stuff is. So that's why this drops out to 0 and this drops out to 0. And we're left with that C2 is equal to 0. And then here, EI times V of, 40 is equal to 0. Or, it's really V of 40 is equal to 0. I'll come back to explain that in a second here. So V of 40 is equal to 0. And we use the same equation again in this case. We're not using the slope equation up here, which sometimes we do, sometimes we don't. Same equation, but we're evaluating it at a different value of x. So in this case, now I have negative 5 over 3 times 40 cubed minus 20 over 3 times 40 minus 20, which is 20 cubed, plus here, I'm going to have 40 minus 40 is 0, so this term will drop out. And I'll have plus 40C1 plus C2. Two equations for my two unknowns, C1 and C2. From the first equation, I know C2 is equal to 0. So I can reflect that now in my second equation. In this equation now, the only thing I don't know is C1. So I can use equation number 2 to solve for C1. C1 is 4,000. Final step, now that I know what my constants of integration are, I can come back to these equations and either rewrite them or modify them. I now know this is 4,000, and that's 4,000x, and the C2 was 0 in this case, so I don't have to write it in my last equation. Final step for this one, I was asked to find the deflection equation V of x. So V of x is going to be 1 over EI times the stuff that's over here. So 5/3 x cubed minus 20/3 x minus 20 cubed plus 55 over 3 x minus 40 cubed plus 4,000x. So really all I did was I divided through both sides by 1 over EI. That way this is the deflection measured in meters, or in this case it would be in inches. as long as this is where my units being consistent are crucial. If I'm working in inches, I want deflection in inches. This has to be in inches to the fourth, and then this would have to be in PSI, and then all of this had to be measured in pounds. So the unit consistency you have to be very careful of here. So this would be my final answer.